In this lab, the goal is to examine both the pendulum and spring oscillation motions of a spring mass system and to compare the motion data with a Python model using physics principles. The result is that the model proves to be accurate in predicting the actual observed motion, and in this report I will explain the method and analysis of the comparison. The physics principles that I use in this lab include Newton's second law to determine each new velocity according to the net force, the energy principle, which we use to determine whether the change in kinetic, gravitational potential, and spring potential all add up to the total change in energy. Other formulas we will use are the gravitational force formula, Hooke's law, and the period of oscillation formula to find K sub s, which is the stiffness of the spring. Some of the conditions for this lab are that all friction will be negligible, the mass of the spring is also negligible. There would be two main forces acting on the mass, the force of gravity and the force of the spring, and also there would be no interaction between the system and its surroundings. To begin, in Tracker I put the origin of the coordinate system on the fixed attachment point with the negative y-axis running downward. I calibrated the distance from the fixed attachment point to the center of the mass to be 0.7 meters. And I set the starting frame of the video to the moment of release of the mass, which was 0.05. When we track its motion, you can see that the mass oscillates in both the x and y directions. Later we will discuss what forces come into play to affect both of these motions. In VIDLE, we must first set the initial conditions, such as the ball's mass, which is taken from the lecture video. The ball's initial position is taken from the tracker data, and we know that the initial velocity is 0 since the mass is released from rest. Next, moving on to the conditions for the interactions, we specify the g constant of 9.8 meters per second squared. K sub s we find by rearranging the oscillation formula. A good estimation of the period of oscillation t we can find by going to Tracker and taking the total duration of 3 periods and dividing it by the number of periods, which is 3. As you can see here, the duration at this point is 4.558. If we divide that by 3, we get 1.519. Then we just plug in the t value and the mass of the system to find the stiffness of the spring. To find the length of the relaxed spring, we can set the magnitudes of the force of gravity and the force of spring equal to each other, since we know that these both add up to 0 when F net is 0 at static equilibrium. If we set the calculations of each force's magnitude equal to each other, we can then solve for L0, which gives us 0.127 meters. Next, I define L to be the distance between the ball and the attachment point of the spring, L hat as L over the magnitude of L, and S as the distance that the spring is being stretched. Since in this lab the mass will always be pulling down on the spring due to the force of gravity, S will always be positive. Then I listed the initial energies as well as the energy changes of the kinetic energy, gravitational potential energy, and the spring potential energy using the formulas that I listed earlier. When we run our model, we can see the two main forces coming into play. The weight force, or the black arrow, is constant and it's always pointing downward. The spring force, however, is always pointed towards the attachment of the spring, and it increases as it is stretched, which makes sense since S is getting larger. The net force here is signified by a yellow arrow, which is always pointed towards the position the mass would be in at static equilibrium, and the force gets larger as the distance gets farther away from the center. Also see in these graphs that the blue line signifying the prediction of the x and y motion is actually very accurate when it's predicting the y motion. However, there's some discrepancy when it's predicting the x motion, and these discrepancies are most likely due to friction causing the system to slow down, and also human error when tracking the video's motion. When we graph all the energy changes and the total energy change, which is signified by the yellow line, we can see that the energy principle is satisfied in our model since the total energy change is 0 throughout the duration of the motion, which is true because there are no interactions with the surroundings. Finally, to analyze the difference between the periods of oscillation in the x and in the y directions, the difference is that the period of the y motion is related to the spring mass oscillation and is therefore dependent on the mass of the system as well as the spring stiffness. The period of the x motion, on the other hand, is associated with the pendulum oscillation and is affected by the length of the pendulum as well as gravity.